Yeah, our second talk this morning is Bob Haslhofer, who will tell us about classification of non-collapsed translators in R4.
Yeah, thanks a lot, Jonathan and Matt, for organizing this really nice conference. So I want to talk about this joint work with Choi and Hershkovits about classification of non-collapsed translators in R4. Start by reminding everybody, so we all know that. So given an n-dimensional surface in Rn+1, we can evolve it by mean curvature flow. So the evolution equation is just that at each point x on the hypersurface, the normal velocity is given by the mean curvature vector at that point, and that gives this one parameter family of hypersurfaces MT. So for example, in the picture here, you see a mean curvature flow through a non-degenerate neck singularity. Okay, and of course, mean curvature flow, like most nonlinear PDEs, forms singularities. The most well-studied ones are neck singularities. So let me tell you more precisely what I mean by neck singularity. So let curly M be a mean curvature flow, and let capital X not be any point in space-time, and let lambda I be any sequence of rescaling factors going to infinity. Then we can consider this so-called tangent flow at X0. So just take the flow and shift it in space-time so that X0 becomes the new center of the universe, and then parabolically dilate by those factors lambda I, meaning you rescale space by lambda I and time by lambda I squared. And then along a subsequence past a limit, and any such limit is called a tangent flow at X0. And it's a basic fact due to Huysken's monotonicity formula that those tangent flows always exist and they're always self-similarly shrinking. And this neck singularity, I mean that some and thus actually any tangent flow at X0 is this round shrinking neck. So it's a cylinder with one R factor, so R times Sn-1. But it turns out when you solve this ODE, the radius is just given by this square root here. Good. Okay, so that's the assumption of a neck singularity is captured by the tangent flow at X0. Good. Okay, and mean curvature flows through neck singularities is by now very well understood. So essentially everything that can potentially happen is captured by three potential scenarios. I'm going to tell you now the non-degenerate neckpinch. We've already seen that, and then there are two others, the degenerate neckpinch, and potentially there could also be an accumulation of neckpinches. Okay, so the first one we've already seen. So in this standard dumbbell picture, this neck pinches off, and when you blow up at the singularity, then you just see this round shrinking cylinder R times Sn-1. Okay, and then probably also most of you know there's a variant of this example where the two spheres don't have the same size, but you make one sphere smaller. If you make it very small, then it just moves through the neck before the neck pinches off, and there's no singularity at all. And if you make it large enough, then you see this standard non-degenerate neck pinch. But then in between, there's a borderline case when the sphere shrinks exactly at the same time it moves through the neck, and then you see this degenerate neck pinch. And when you blow up along a suitably chosen sequence of tip points that kind of follows the cap, then as a blow up limit, you get this translating ball soliton. So that's a self-similarly translating solution of the mean curvature flow, and it looks like in the pictures it opens up like a parabola. Good. Okay, and potentially, okay, that's an open problem actually, but potentially there could be a third scenario. So you could imagine, well, maybe there's countably many neck pinches, and so then you would decompose your surface into countably many pieces, and each of them, let's say, becomes extinct in a round point. And if that happens, then you could pick a sequence of space-time points and scaling factors, and construct a blow-up limit in such a way that, like at small scales, you see those spheres, but at larger scales back in time, you see the cylinder, you see the neck, and then as a blow-up limit, you would get the ancient ovals. So that's as we've seen, that's an ancient solution that interpolates between the sphere and the cylinders of a.
Is this happening at the same time, Bob, or at different singular times?
That would be at slightly different times. So you can't see them at a special blow-up limit as at the first singular time. So. Okay, yeah. So it becomes extinct in around point, but at negative times it looks like a long cylinder with two ball solitons attached. And right, so the classification theorem that we proved was K-Young's and and higher dimensions prime also helped us, since that, well, any blow-up limit near any neck singularity is one of the following 5 things. The first two are kind of trivially a static plane, so that happens just if you rescale by too much. Round shrinking sphere, and the interesting 3 are the round shrinking cylinder and the translating ball soliton and the ancient ovals. So in fact, that's kind of a corollary. So the classification theorem, as Natasha also mentioned in her talk that we proved, is as well that any ancient asymptotically cylindrical bracket flow is either a round shrinking cylinder or a translating ball soliton or an ancient oval. So the only thing we assume is that the tangent flow at time minus infinity is this neck. Important special cases of this classification theorem have been proved in earlier work by many people. So first of all, there was a paper by Shusha Wang where he classified 2-dimensional convex entire self-similar translating solutions, and then many people contributed. So in particular, this Bernstein-Wang theorem, so they only assume low entropy and self-similarity, but they didn't assume convexity anymore. And then also more recently there was this breakthrough by Brendler, Choi and Hershkovits, where they still assume convexity and non-collapsing and so on, but they don't assume self-similarity anymore. So they can look at all ancient solutions. And so finally in our theorem, the key point is that we don't assume anything, so neither self-similarity nor convexity, and still get the classification. And that's of course important when one wants to understand all those neck singularities, because, well, if one blows up along a changing sequence of points, then one doesn't get self-similarity anymore. So Huysken's monotonicity formula only tells you what happens when you blow up around a fixed center point. And also, well, convexity, the mean convex neighborhood conjecture is what we wanted to prove, not what we wanted to assume. So therefore, it's important that this classification theorem is in this very general setting. Okay, good. But by now, those neck singularities are very well understood. Okay, so that was kind of the 10-minute summary of the talk that I gave like 1 or 2 years ago, usually when I give a talk. Okay, good. Any questions about neck singularities? Good. Okay, so then let's move on to the newer stuff. So now instead of necks, we want to understand bubble sheets. Okay, so for concreteness, let's focus on 3-dimensional mean curvature flow in R4. And then, well, if the flow has a cylindrical singularity at some space-time point x0, then there's 2 cases. So there's this case of neck singularities that is now well understood, and the other case is the case of so-called bubble sheet singularities. So that means that you have this other cylinder, which is R2 times S1. Okay, so maybe you might say, well, that looks like a minor difference. Here it's R times S2, and here it's R2 times S1. What's the big deal? But actually, it's a huge difference. And for those neck singularities, at the end of the day, all of them turned out to be rotationally symmetric, and that's why we got a short list classifying all of them. But in this bubble sheet case, it turns out there are actually examples that are not rotationally symmetric. So it's a fundamental new challenge to classify them. Good. So let me give you one example of a bubble sheet singularity. So for neck singularity, we have this example of the neckpinch. Now for the bubble sheet singularity, we have this discpinch singularity. So the picture is like you have this two-dimensional disk times S1. And then the radius of the S1 depends on the position. So the radius of the S1 is smallest here, and the center of the disk, and it becomes larger if you move away from the center of the disk. And so that's a rotation, that's a circularly symmetric example. And then well, at some time this S1 at the center of the disk will shrink to a point, and then it forms a singularity there. And so then then afterwards it evolves like indicated here. So here the evolution is modeled by R times the two-dimensional bowl. So if you look at the scale of the bowl, then this S1 here looks almost like a straight line. Good. Okay, so that's the simplest symmetric example of a flow through a discpinch singularity. Good. Okay, and in general, our goal is, well, we want to understand those bubble sheet singularities. Good. Okay. So while those neck singularities have been analyzed by many people over the last 20 years, and where our classification theorem is kind of the final theorem of the story, the analysis of those bubble sheet singularities until recently seemed to be out of reach. And so in today's talk, I would like to describe joint work with Kayans and Orr, where we classify all non-collapsed blow-up limits in R4, assuming self-similarity. And so let me also mention that's part of a larger classification program for all ancient non-collapsed flows. So eventually we will remove this self-similarity assumption again. And so this classification program was introduced by Kayans or and myself, and also by my student Wen Kui and myself, and there's also work in progress with Kayans and Orr, and also with Bomchen and Totti and Wen Kui and Natasha. Okay, so here's a slide of all my amazing collaborators who have my lot with working on ancient solutions. Okay, so that's Kayans and Orr, and that's Wen Kui, and and you of course all know Natasha and Totti and Bomchen also. So today's talk is mainly about the joint work with Kayans and Orr, but then actually with Wen Kui, I have a paper which is called Hearing the Shape of Ancient Non-Collapsed Flows in R4. So that's actually the paper where we introduce the classification program and break it up into different cases. And then in the compact case, Natasha and Totti and Bomchen also join. Okay, so for this talk, we focus on the case where we assume non-collapsing and self-similarity. So let me remind you what those two assumptions mean. So let's take any ancient flow in R4, and so then this non-collapsing condition means that the mean curvature is positive, and that every point admits interior and exterior balls of radius at least some constant alpha divided by the mean curvature at that point. Okay, so actually follows ancient solutions. Yeah. It always works with alpha equal to 1. Good. Okay, and all blow-up limits of mean convex mean curvature flow are non-collapsed, so that actually goes back to the work of Brian White, and more generally by Ilmanen's mean convex neighborhood conjecture that we recently proved in the case of neck singularities, but not yet for bubble sheet singularities. It is actually expected that the blow-up limit near any bubble sheet singularity will automatically be non-collapsed. So hopefully in some years that will not be an assumption anymore, but a conclusion instead. Good. Okay, so that's non-collapsing, and the other assumption for the moment is self-similarity. So mean curvature flow can be self-similar, in particular in those two different ways. So it can be self-similarly shrinking, so that means that at each negative time, the time t slice is just given by this scaling of the time minus 1 slice, or equivalently the time minus 1 slice solves this elliptic equation. Or it can be self-similarly translating, so then mt is just m naught plus t, and let's assume without loss of generality it just translates with unit speed in E1 direction. And then it will, then any slice will solve this elliptic equation, the translator equation. Okay, and so those self-similarly shrinking solutions, they're actually easy to understand. So that's, yeah, so that essentially goes back to the early work of Huisken. So after splitting up some R factors, it's just like, well, convex guys always converge to a round point, and if it's already self-similar, then it's just a round sphere. Okay, so the shrinking case is easy. But those type 2 blow-up limits, those so they are self-similarly translating, so like, at least when you blow up in a la Hamilton, like in the degenerate neckpinch, when you blow up along those maximal curvature points, then you get a self-similarly translating solution, and so more generally we expect, even if you don't blow up a la Hamilton, blow up along any sequence of points and with any rescaling factors, then we expect it still will be self-similar translating if it's strictly convex. So you have to exclude this silly example of R times 2D over. Let me tell you what are the known examples. So we look at ancient flows in R4, and we assume they are non-collapsed and self-similarly translating. Okay, so then the two easy examples are the rotationally symmetric 3-dimensional bowl soliton and R times the 2-dimensional bowl soliton. But then actually Hoffman-Ilmanen-Martin-White found a 1-parameter family of solutions that interpolates between the two. So you can think of them like you can think you start with the round 3-dimensional bowl soliton. So then the level sets here would just be round spheres. But now you deform the round spheres into ellipses or ovals. Okay, so then if you make them more oval, then you get those HIMW examples, and then you can make them more and more oval, and in the limit where this eccentricity goes to infinity, you would converge to R times the 2-dimensional bowl. So that's how you can think about this 1-parameter family interpolating between those two solutions. And so actually they didn't describe them in terms of eccentricities, actually they described them in terms of the principal curvatures at the tip. So the principal curvatures at the tip, if we normalize it as unit speed, then they're k, 1 minus k over 2, 1 minus k over 2, where k is between 0 and 1/3, and for k equals 1/3, well, it's the round 3-dimensional bowl, while for k going to 0, it converges to R times 2-dimensional bowl. Yeah, I think some of those examples are also in the paper of Shushavan, but Hoffman-Ilmanen-Martin-White really constructed the whole 1-parameter family of solutions that we need.
So those are sort of constructed or classified in terms of their curvatures at the tips. Is there a sort of complete description of the asymptotics? Say if you take a family of normals, or converging to a normal at infinity, can you sort of up to scaling say that it has to be this, so it'll be a bowl across a line, I guess, but can you sort of classify them in terms of the asymptotics in that way?
Yeah, so you will see what the asymptotics are as a consequence of our classification.
Yeah. Okay.
But yeah, so Hoffman-Ilmanen-Martin-White, they actually only did existence. So what I just said now about the picture, this one parameter family and so on, it's a bit misleading because they actually that causes a lot of troubles in our proof, right? So from their work, it's not known that for each tip curvature you have a unique one. So you don't know, does it depend continuous? Does the family depend continuously on the tip curvature and things like that?
Yeah. Thanks.
Okay, good. Okay, so our main theorem is that any non-collapsed translator in R4 is either the three-dimensional round ball or at times the two-dimensional ball, or belongs to this one parameter family constructed by Hoffman-Ilmanen-Martin-White, and in particular they are actually uniquely determined by the tip curvature and depend continuously on the tip curvature. Okay, and as a corollary, we get, well, for the mean curvature flow of closed embedded mean convex hypersurfaces in R4 or in any general ambient four manifold, every type 1 blow-up limit a la Hershkovits, well, that was known long before either the round shrinking S3 or the round shrinking neck or the round shrinking bubble sheet. And then the new part is every type 2 blow-up limit a la Hamilton is either, well, the three-dimensional round ball or the R times two-dimensional ball, or it belongs to this one parameter family of oval balls constructed by Hoffman-Ilmanen-Martin-White. Okay, and good. Okay, and the reason why I really like this theorem is because, or this corollary also, is because it kind of breaks the dimension barrier. So up to now, usually all classifications of blow-up limits, well, they were either in the two-dimensional case or in higher dimensions, assuming two convexity or neck singularities or something like that. And there's a similar story for Ricci flows, or either assuming three-dimensional Ricci flow or assuming positive isotropic curvature, which morally corresponds to two convexity. And so this seems to be the first result that moves beyond this neck or two convex case. Good. Okay, so let me give you some idea of the proof. So I mean, it's a long paper. It's almost 100 pages, but roughly speaking, there's 5 key steps. So first, to figure out what is the blowdown and establish circular symmetry, and then get some uniform sharp asymptotics. Okay, so that will answer the question of methods, and then we have prove something which we call spectral uniqueness, and then there's 2 more steps to actually go from the spectral uniqueness result to the classification result.
I assume some of those steps are not dependent on this dimension, is that right?
Yeah, I mean, with minor modifications, I think everything would work in the 3 convex case.
3 convex, yeah. Okay.
But without 3 convexity, even the first step is quite unclear to understand the blowdown.
Okay, thanks.
Right, so maybe before I really start talking about those 5 steps, let me first give you some potential scenario you have to worry about. So when one has to worry, well, you know, like R times the 2-dimensional bowl, that's a perfectly valid solution of the mean curvature flow, right? So then one has to worry, well, could it be that there's some translator, some ancient solution of the mean curvature flow that asymptotically looks along those sides like R times the 2-dimensional bowl over here and R times the 2-dimensional bowl over here, and then they're kind of glued together and completed to a solution that looks like this wing. So I mean, there are there are those wing-like flows in the collapsed case, right? And then one has to worry a lot. Well, is there any ancient non-collapsed wing-like flow? And so that would make a classification quite hard, or maybe impossible. Right. So the first thing we actually proved is those ancient non-collapsed wing-like flows. They do not exist. Okay.
Sorry to interrupt again, Bob. So I think Shuja in his paper conjectures that if the gradient goes to infinity everywhere, it has to be the bowl. So I guess that's not true then. Is that right?
No, it's not no, for those Hoffman-Ilmanen-Martin-White examples, the gradient also goes to infinity.
Yeah, okay.
So we proved that so those wings don't exist, so we proved that the blowdown is always a half line. So in particular, I mean, it holds for all ancient non-collapsed flows, but in particular for translator, if you assume it's strictly convex, and let's assume it positive, translates in positive E1 direction, then the blowdown is just this half line, the positive x1 axis. Okay, so the blowdown is always a half line. The blowdown is never this wedge, never this triangle. Good. Okay, and the particular ones we know this blowdown, then it's a corollary. It has a unique tip point, and this is SO2 symmetric. So that was this SO2 symmetry was also proved independently by student of Brendle. Good. Okay, so let me just give you the rough idea how we roll out those wing-like flows. So the idea is, well, if you had such a wing-like, if you had such a wing-like flow, well, then you could blow up. So if you had a flow where the blowdown is a triangle, then you could blow up along those sides. So if you blow up along those sides, well, then it must split off a line, so it must be R times something. Those two-dimensional guys are already classified, so it must be R times two-dimensional ball here and over there. But then we have something which is called the fine bubble sheet theorem. So this tells you, well, if you look at those R2 times S1, then those S1s, they don't have all exactly the same radius, but the radius changes slightly if you go along the bubble sheet. And the fine bubble sheet theorem tells you, well, there's a unique direction in which the radius of those S1 factors increases. But here it would increase this way, well, here it will increase in some other direction, which contradicts our theorem that those S1 factors increase in a unique direction. Good. Okay, so that's the first important step to get started, understanding the blowdown and the SO2 symmetry. Good. Okay, so then the next step is to establish some uniform sharp asymptotics. Okay, so to this end, we consider those level sets. So M was this three-dimensional translator. So if you look at the level at some fixed height h, then you get some two-dimensional surface sigma h. And it's also, as we've seen, this surface sigma h is SO2 symmetric. So that's really described just by a profile function depending on one variable y and then one time parameter tau. Okay, and it turns out that those two-dimensional surfaces sigma h, they satisfy exactly the same sharp asymptotics as the two-dimensional ovals in R3 that Natasha talked about. So you have to set time equal to minus the height, and then you can write it down in rescaled variables where tau is minus log of the height and y is this rescaled position, and then you get the same asymptotics that Natasha already mentioned. In particular, if you look in the middle, so there you see the cylinder, but then so the cylinder of radius squared of 2, but then it deviates by this inward quadratic bending, this minus y squared over tau. So that's how the ovals look in the middle, right? So you have the cylinder of radius squared of 2, but then you have this inward quadratic bending, this is precise coefficient 1 over square root of 8 times tau. Okay, and yeah, so for this, the idea is roughly, well, from the first step, we already know we have vanishing asymptotic slope because the blowdown is just this half line, right? So it has vanishing asymptotic slope. So roughly speaking, our mean curvature flow looks like R times, at least at high levels, it almost looks like R times some two-dimensional flow. So roughly speaking, those level sets evolve by some perturbation of mean curvature flow, and that's why we get the same sharp asymptotics. Good. Okay, so then the next step is what we call the spectral uniqueness theorem. So let's take two non-collapsed translators. So we have to normalize and center them suitably, and then if their profile functions at some very negative time satisfy some spectral condition, then we can conclude that the translators are actually the same. Okay, so let me explain what is the spectral condition. So the analysis of this profile function is governed by this explicit one-dimensional Ornstein-Uhlenbeck operator. So this drift Laplacian here on this Gaussian L2 space. And well, for this operator, you can explicitly compute all the eigenvalues and eigenfunctions, and there's just those two unstable eigenmodes and one neutral eigenmode, and all other ones are stable. Okay, and the spectral condition is that, so if the projection to the unstable and neutral mode vanishes, then we can conclude that the solutions are equal. Good. Okay, and yeah, so to prove the spectral uniqueness, well, we combine energy estimates as in the work that Natasha explained, and that's kind of not a full answer yet. So those energy estimates, they work well at high levels, and they work well if you are far away from the cap region. But then one needs something else to deal with the cap region, and there we use the maximum principle and some barrier estimates. Good. Okay, but combining those two things, we get spectral uniqueness. Good. Okay, so then the last two steps is, well, how to actually go from the spectral uniqueness to classification. So that's somehow quite a bit harder in the translator case as compared to the oval case. So in the oval case, remember Natasha also told you, well, there are those parameters, but in the oval case, it's relatively easy. There one can just, well, do some recentering and some parabolic rescaling to ensure that those spectral conditions are automatically satisfied. And that's because, well, up to translating and parabolic rescaling, there's only one oval solution, right? But now for those translators, we actually don't have one solution, but we have a genuine one parameter family of solutions that can't be transformed into one another just by some symmetries or rescaling or something. So it requires other methods to actually ensure that we get those spectral conditions. Good. Okay. Right. Yeah. Okay. So this P plus, that's kind of trivial, right? So this P plus condition you can always ensure just by translating in the x1, x2 planes. So, but then the hard condition is to ensure this this neutral mode condition. So this neutral mode condition, that's the inner product with this eigenfunction y squared minus 2. So intuitively, that kind of measures the eccentricity, like how much your oval or ellipse is bending inwards, right? Good. Okay, so yeah, so to analyze this neutral mode projection condition, we consider what we call the eccentricity map. So that takes any Hoffman-Ilmanen-Martin-White translator and maps it to this number, well, which is the Gaussian inner product of its profile function with this neutral eigenfunction 2 minus y squared. Okay, so and if you have a translator that exactly satisfies the sharp asymptotics without any error terms, well, then you can compute what is this number here, and then it would be this number. Then we prove for any nearby number x, so kappa is some small number which measures the error term. For any nearby number x, we can actually find some Hoffman-Ilmanen-Martin-White translator which has this eccentricity equal to x. And we can do this while at the same time preserving the sharp asymptotics up to a small error kappa. Okay, so the basic idea is, of course, just to do some continuity argument in this ellipsoidal parameter of this Hoffman-Ilmanen-Martin-White construction, right? So you kind of have this one parameter family. So if you are close to r times 2d bold, and the eccentricity is huge, right? So if you are close to the three-dimensional round ball, the eccentricity is small, and somewhere in between there must be some guy which has the correct eccentricity. But then one has to do this very carefully to ensure that along this continuity method, one doesn't leave the range where the sharp asymptotics still hold uniformly. Good. Okay, and finally we have to relate this eccentricity at some high level with the principal curvatures at the tip. Okay, so to this end, we look at what we call the tip curvature map, so which just maps this Hoffman-Ilmanen-Martin-White translators to their tip curvature, smallest principal curvature at the tip, and there we prove that this tip curvature map is monotone and analytic, and so hence it's strictly monotone and thus bijective. So for monotonicity, the idea is to use some Rado type argument, so that goes back to the classical theory of two-dimensional minimal surfaces, right? So that's those kind of arguments like, well, how often do minimal surfaces intersect? And so in our setting, well, we have three-dimensional hypersurfaces, but they are SO2 symmetric. So the two-dimensional argument still works in our setting. And so the basic idea is just, well, those HMW translators, they are constructed as limits of translators with boundary given by ellipses, right? And so ellipses in the plane, that's quadratic equations, so they intersect in 4 points. And then you can use this to find out, well, what's the touching order at the tip. And so that's how we get that the map is monotone. But that only gives weak monotonicity. So no strict inequality, because one has to pass to the limit and the height goes to infinity, and then there's more work to show that this tip curvature map is actually analytic, so that's kind of standard, but also quite long, so that uses Lyapunov-Schmidt reduction and a suitable linearized version of the estimates from before. Good. Okay, but then combining all those steps, one indeed gets the classification result. Okay, any questions about the outline of the proof?
Just on the previous slide, what does monotone actually mean here?
Oh, so at this stage, we already know that this family is homomorphic to an interval.
Oh, okay.
Okay, yeah, right. I forgot to say that. Yeah. So it's a map from an interval to an interval. So monotone just means the standard thing. Yeah. So we already know it's homomorphic to an interval, but the remaining question in this step is like how do we parameterize this interval geometrically, right? And so Hoffman-Ilmanen-Martin-White, they parameterized geometrically in terms of the principal curvature at the tip. So we wanted to relate to their parameterization and not describe our result in terms of some other weird non-geometric parameterization. That's I mean this eccentricity, that's a kind of less geometric, more analytic way to parameterize them. No, it depends on the choice of some height where you compute this inner product. So the outlook is, so for today I mostly focused on this non-collapsed self-similarly translating case, but in work in progress with K-Youngs and Orr, we show that one can actually remove the self-similarity assumption. So that's actually a consequence and not an assumption. Then for the talk, I focused on the non-compact case, but you, of course, can also ask what is happening in the compact case. So then, as Natasha already mentioned in joint work with Venquevi, in the compact case, on the one hand, we proved uniqueness, assuming the symmetry, but on the other hand, we also constructed this one parameter family of examples which have reduced symmetry. So that's kind of a compact version of this HIMW family. Good. I can't. Yeah, and we expect that's it. So the classification is work in progress with Bomchen, Totti, Venko, and Natasha. And then, right, so yeah, so typically for two convex, typically people first classified stuff for two-dimensional mean curvature flow and then generalized it to the two convex case in higher dimensions. Similarly, here it's expected that, well, once you understand it in R4, it will also hold in the three convex case in any dimension. And so finally, there's always a very nice correspondence between mean curvature flow and Ricci flow. So in particular, it's very natural to conjecture that similar classification results will hold for Kappa solutions in four-dimensional Ricci flow. In particular, in the spirit of today's talk, I believe that every non-collapsed steady soliton with non-negative steady Ricci soliton with non-negative curvature operators, either the four-dimensional prime soliton or times the three-dimensional prime soliton, or belongs to the one-parameter family of steady solitons constructed by Eli. But some of the techniques we used are very specific to mean curvature flow. So for the Ricci flow, new methods need to be developed. Okay, good. And I think I'm gonna stop here.
Great, thanks, Bob. Do we have any questions?
Bob, do you expect in general the non-collapsing translators will always blow down to a line segment, a half line, or that you could get sort of flying wings in higher dimensions, non-collapsed wings?
Yeah, so let's assume they're strictly convex, otherwise the split off.
Sure.
So I mean, it's tempting to conjecture that the blowdown should always be a half line, but I think that's very hard to prove.
Interesting. I have another question about convexity, whether this is sort of resolved now, convexity of these examples. Because the Hoffman-Ilmanen-White examples, the convexity wasn't known, at least when their paper was published. They constructed them as graphs, so they were automatically mean convex, but whether they were convex, I think, was not known.
Yeah, but that's easy. I mean, they're non-collapsed, right? And then just by the convexity, they must be convex. But yeah, I think in that paper it was also not really written down that they're non-collapsed. So. Right. That's, I mean, non-collapsing one can see in several different ways, like you guys proved that it sweeps out all space, right? We wrote some other argument, like just using the methods of Brine-White, right? Then I think Keaton and Seaman have yet another proof how one also sees that they're non-collapsing.
Right. Yeah. Thanks. That's a good point. It would be nice to have like a direct convexity estimate as well, I guess. But
with the general case where you don't assume self-similarity, are you willing to tell us any ideas about how to do it? Yeah,
sure. So I mean that right. So So I mean, one problem is like there's no good general mechanisms to prove that something is a translator, right? So not like Huysgen's monotonicity formula is a general tool to prove that something is shrinking, but to prove that something is translating, that's more difficult. So that basic mechanism is if you look at our mean convex neighborhood conjecture paper, so there we proved something which we call the fine neck theorem. So that tells you, well, that all those necks, they open up by so there's some fixed constant, some universal constant of the flow, which tells you how those fine necks open up. And then if you integrate this fine neck theorem, well, in the neck case, you see, well, things must open up like a parabola, and if you work a bit more on that, you see translating whole solitons. So the fine neck theorem is actually something which allows you to prove something is a translator. But then in this bubble sheet case, it's to leading order one doesn't see this fine neck theorem anymore, because to leading order one sees this inverse quadratic bending of the ovals. So what we have to do is we have to look at the derivative in y1 direction, so that this inverse quadratic bending goes away, and then we have some secondary asymptotics which you can think kind of as a differentiated version of the fine neck theorem, and then integrating that, one gets again that it's a translator.
Sounds tough.
Yeah, so the idea is kind of similarly like with the fine neck theorem, but it's much more technical, because to leading order one has this inverse quadratic bending, so we have to look at those secondary asymptotics instead.
Sure. And all through this, you don't yet know that the curvature is actually bounded on a given time slice, right? So I guess that will come out at the end.
Yeah, I mean, right. I mean, yeah. Once you know something about the asymptotics, you know that. Yeah. Mm-hmm. But yeah, you don't know it from the very beginning. That's true.
Okay.
It's a good time to wrap up the session. Thanks, Bob.